Okay, good morning, everyone. So this is the last Compton lecture of the spring, so I wanted to make a couple of quick announcements. So first, I wanted to thank all of you for being here through the whole series. We couldn't do it without you. I wanted to thank Christoph for giving a wonderful series of lectures. Today's is a great topic, so it'll be very interesting. I also wanted to thank Mary Heinz, who all of you see every week, who makes things run very smoothly. And then two other things. I think all of you know, after the lecture today, there'll be lunch upstairs in room 206, so I hope you'll be able to join us. And finally, I wanted to tell you about the lecture series that's planned for the fall. So we have a speaker. It's Anthony Badia, who's a Schmidt Fellow. These are fellows who have been brought to the university to work in different areas of science, but specifically applying artificial intelligence. And so he's going to give a series of lectures. He's a particle physicist by training, so he's going to give a series of lectures focused on questions in particle physics, both the science questions and how the experiments are done, but he's going to talk particularly about how new techniques in computing and artificial intelligence are changing the experiments and how we do them. So I think it'll be a fascinating series. So I hope we'll see all of you in the fall. Okay. Oh, I don't remember. We'll send it out and announce it. It'll be the Saturday, at the end of the first week of the quarter. But I'm afraid, so it's probably September 30th. Okay. So right around end of September, early October. Yes.
One quick one. Now that the University of Northwestern and the University of Chicago have classes and they coordinate, are you guys working on projects together now also? Experimental projects?
Oh, I think there are lots of, individual areas of collaboration among faculty members. There's a new, NSF-funded physics center that's being done, jointly with Northwestern. But I think most of the collaboration is at the level of particular faculty members that work together. But there are lots of collaborations between the two groups. So that's a long discussion. But there are many individual things, but there are not too many university-wide programs that are done together, as far as I know. Okay, thanks, Chris.
Okay, this works? Good. Okay, welcome to the last lecture. One more to go. So, this one's going to be about gravitational waves. And if we want to talk about gravitational waves, you probably want to start with the gravity part. So all the way 8 weeks ago now, I talked about this guy, Isaac Newton, and he, first of all, he came up with his laws of motions and also his theory of gravity. And I kind of want to start there, but actually not with this part, but with this one, that an object, unless you apply forces to it, will keep moving in a straight line. But we have to think a bit more about what exactly we mean by straight line, which turns out is actually kind of a harder question than you'd think it is. And kind of if you want to go all the way back to the start of geometry, you have this guy who may or may have not actually looked like this, Euclid, who kind of started this field of geometry. And if you want to start a new field of math, what you want to start with is, first of all, he defined a bunch of things like what do I mean when I say a line, what do I mean when I say a point, and so on. And then he started with axioms, which is basically assumptions that you don't prove, you just kind of assume they are true, and that's kind of your fee to entry, so to speak. Like if you don't accept this, then you have to kind of come up with your own math. But there are pretty simple assumptions. So first of all, if you have 2 points, you can always draw a straight line between them. That's fairly clear, I think. If you have a line that has a certain length, you can always extend it as long as you want. You can always draw any circle around any point with any radius you want. Fair enough. And if you have 2 right angles, they're always the same angle, basically. And that's his first 4 axioms. And then the fifth one is, if you have a straight line that crosses 2 other lines, and the interior angles of the lines are less than the 2 right angles, the lines will intersect if you just draw these lines long enough. So what does this mean? So basically it's pretty simple. So you have a line here, you have two lines crossing, you have these two angles here, and if you add them up, they're less than 180 degrees in some. So if you extend these lines long enough, they will cross eventually. Now, you can probably tell one of these 5 is different than the other ones by the fact that I just had to put up an entire new picture to explain it. And this was kind of weird, and you can kind of tell that Euclid also thought it was weird, because then in his book, he basically first tries to do everything he can with just the first 4, and then eventually starts, okay, now if I take my 5th axiom into it, what can I do then? But for about 2,000 years, this was kind of something, people were kind of bugged that this one was so weird, but you still apparently needed it. So a bunch of mathematicians tried to find a way to just basically prove that this is true with the other 4 axioms. But nobody managed to. It was just something that, this kind of weird feature in geometry. Is that the question?
Yes. In terms of space and determining the distance between, let's say, the Earth and an object that is hundreds of light years away, is it assumed that there is a straight line traveled by light from the Earth to...
That's exactly what I want to get to now. Okay. So, for 2,000 years, this axiom just kind of hung around and was kind of awkward until in like early 1800s, late 1700s, people figured out that actually, what if it's not true? And the first one to kind of work with this was Nikolai Lobachevsky, a Russian mathematician. And a good example of this is basically if you try to draw a very big triangle on the Earth, you learned in school that if you draw a triangle, all the angles should add up to 180 degrees. But you can just go east very far, then go north to the North Pole, and then kind of go back, and then you can easily draw a triangle with basically any sum of angles if you want to. And this is what's called non-Euclidean geometry, because it turns out you can actually get rid of this axiom that with parallel lines, and you get something consistent. It's kind of weird, but it works. Like you don't have any contradictions or anything like that. Another mathematician, Bernhard Riemann, came up with a very useful way to think about this, and that is something called a metric. And the idea is basically you want to answer the question: if I am somewhere and now I'm moving some distance, or like a small distance in some direction, how far have I moved? And for Euclidean space, that's this pretty well-known equation. I just basically, for example, I move a little bit east. Let's just say like this direction is east. It probably is. I don't know. If I just move some direction, I will just add up the square of how much I moved east, how much I moved north, and if I somehow fly, then how much I moved up. And I square those, and then I take the square root. So that's how it works in Euclidean geometry. And in this, if I just want to go like over here, then I will go then a straight line, because that's fairly obviously the quickest way to go. But if I now want to go really far east, so if I want to go to, let's say, Rome, which turns out is actually pretty much exact, or almost exactly the same latitude as Chicago, I'm not going to go straight east. I'm just going to go this kind of weird-looking circle. If you look at the globe, this is fairly easy to figure out why it looks that way. You can just take a piece of string and just put it over the globe. But if you now imagine like you have someone who just has no concept of like what a sphere is, who cannot understand that the Earth is actually a sphere, how can you make sense of this? So a way you could think of that is if I the further north I am, if I move, let's say, 1 degree in longitude east, if I'm further north, then I'm actually doing I have to walk a smaller distance, right? If I'm at the North Pole, I can walk around the Earth in like 2 feet, like 2 steps or something. So in that case, you could say, okay, actually, because if you're up here, walking east is shorter than down here, it actually makes sense to, first try to go a little bit north, and then, try to do a big part of your travel further, where the metric now tells you that actually if you walk east, it's a shorter distance, and then you kind of loop back around. So that's how you can think about these that's how mathematicians describe these non-Euclidean geometries. And then what you basically say, you say, okay, what I mean by a straight line is actually, it's just, if I have 2 points, then the shortest path between them is just what I call a straight line, except I don't call it a straight line, then I just call it a geodesic, which is just a word for the shortest path between two points. And now this is then where general relativity enters the picture, because it actually turns out that if you have gravity, then you live in this non-Euclidean space where you have to think about this in terms of metric. So the idea behind relativity is you can actually boil it down to just 3 assumptions. So one is, if you have 2 reference frames, then both are equally valid, and in both you will see the same laws of nature. So the classical example is, if I'm standing here and I see someone sitting on a train that's going really fast, I see that we're both in inertial reference frames that are, both perfectly valid. We will both see the same laws of nature, and it's going to be consistent. And the next one is that the vacuum speed of light is always the same speed in all the reference frames. So if I measure this, if that person on this other train takes out a flashlight and shines a light somewhere, I will see it move at the same speed as the person on the train. And then what Einstein added for the general relativity is that it is impossible to distinguish between being in a gravitational field and being accelerated. So if one day you wake up in a little box and you feel gravity, then there's actually no way for you to tell really if you're not in outer space where far away from the Earth, from any source of gravity, but you're on a spaceship that's accelerating. There is, at least locally, there is no way to tell apart. If there's a window and you can look outside, there's ways you can figure it out. But if you're inside your little box, you cannot tell the difference. And similarly, if you're weightless, it might also just be that you're falling in free fall. And now, Einstein thought about these ideas a bit, and what he figured out that if you combine these, the logical conclusion is that masses must distort space-time around them. And what this basically means is they change the metric around it. So they basically change what exactly the shortest path along 2 points is. And the classical kind of way to illustrate is you have this rubber sheet that's spanned around like a kind of pool, and then you put a big mass in the middle, and it gets pulled down, and then if you roll a marble through there, it's going to get pulled in. I'm honestly not a big fan of this, because it's kind of, the marble changes its path because it's pulled down by gravity, so you're kind of explaining gravity with gravity. But as this comic rightly points out, if you want to go all the way with being completely correct, then we're going to have like 2 other Compton lectures about this. So I'm going to try to take a kind of similar analogy, but that I think is a bit better. And that's it's still not going to be like 100% correct, because I don't want to take out some math and do a math lecture here. But it's going to be kind of close enough. And let's, again, go all the way back to the first lecture and talk about refraction. So what refraction means is basically, if you have a medium, for example, the water in this glass, it will slow down the speed of light in this medium. And this will change the direction of that the light is taking. And that's why you see the straw kind of having this kind of weird bend in it. And the way you can think about this is that light, if you have this like a piece of the straw here and you have your eye here, then light will try to take the shortest or the fastest way between your eyeball from the straw to your eyeball. Now, if the speed of light was constant, again, this would be just a straight line. But because in the water the light is shorter, it actually makes sense for the light to kind of bend so that it that the path it takes in the water is different. Actually, hang on. No, this is the water. So the idea is that if the speed of light changes, then light will move in a different way. It will not move in what we see as a straight line anymore, because there's faster ways for it to take. Yeah, question?
To move from that point to this point, is it a choice of the light ray, or is it controlled by
Yeah, essentially it does, yes.
So in this case, the medium, when it crosses, it's really telling the light ray how to go. It's not a choice of the light, like I want to go from this.
Well, yeah, I mean, sure, like the light can't think. But it turns out the way, like, if you think of it in terms of waves, you can actually show that like light will take the shortest path or the fastest path. That's something you can prove. It's like the light doesn't have to kind of consciously choose it. It's just something it does.
The role of the medium should not be ignored.
Yeah, sure, absolutely. Yeah. Okay. And now let's go back to gravity. So the idea is that as light masses change the metric around them, and this is not only about space, it's also about time. So if you're kind of close to a very heavy object and someone else, really far away, like somewhere over here is looking at you, it will look basically like where you are, the time is slowing down. So if now you want to send a ray of light through here, then it will look to you like the light is moving slower here. But we just said we assume like the speed of light is always constant. So what this means is actually also the space has to be larger here, because it takes we can measure the distance here by just kind of taking the speed of light times the time that the light has traveled. And so if it looks to us like the light is slowing down here, then actually there might be a faster way where you kind of bend around this, and you avoid going into this space here where your metric tells you that it's a longer wait. And then there might actually be two paths, and you can basically have the light bend in multiple ways around the heavy object. And this is actually something we can see. So these are called gravitational lenses. So there is like a heavy galaxy cluster here, and you can see the same galaxy here 3 times. And that is because this galaxy is actually behind the cluster, but the light is kind of bending around this heavy cluster here in the middle. And if this galaxy is kind of perfectly like on a straight line behind another heavy object, you can even see the kind of it getting bent around into this ring. And that is kind of why this bending of space-time can act like gravity and pull things to it. Because if you have a massive object like a spaceship or so, it's a bit more complicated to calculate, but it's kind of doing the same thing where it's basically the bending of space-time changes what exactly the geodesic or the straight line is. Yeah?
Is there any experiment or evidence indicating whether the space-time fabric could be torn or punctured?
I don't know what it would mean if it's torn. It would probably do really weird stuff. I don't know.
Like they say, the wormhole thing.
Oh.
As you go into a wormhole, you got to come out of the wormhole. If it goes to
Yeah.
another part of the universe, how do you get out of the wormhole? Since it bends space-time fabric in both directions, you got to come out of this one and go into that one. You got to have a hole.
Yeah, I think that would be really difficult to observe. So there's probably like some scenarios where you can say like we should see this, but I think it would be really hard to kind of rule out.
Do you believe in wormhole?
Probably not. It's like you can kind of come up with this. You have to make pretty weird assumptions for wormholes to be valid, so probably not. Yeah, there's a question back there.
So I've read a couple of books about string theory, and what I've seen about that is that it's possible, but it also gets weird. And if it could be done without string theory, I would say that you would probably need more matter and energy than is even in the universe.
Yeah, it's well. The problem with string theory, it's kind of not well developed yet. It's more math at this point. So, and yeah, I mean that is one of the problems if you want to build a wormhole. You either need like incredibly big amounts of of matter, or you need like really weird forms of matter, so you cannot really do it. Yeah, back there.
Does the gravitational lensing effect depend on, I would assume it depends on the mass, but does it depend on the concentration? Or is there a calculation so that astronomers can tell how far distance the object behind it's being lensed is?
So interesting, it doesn't actually depend on the kind of the size of the object too much. It's just like what the size of the object, where that matters, is basically just like how close can you get to it. So if you replace the sun by a black hole of the same mass, the Earth would just keep the same orbit. It's just with a black hole you can just get much closer than to a star because it's so small. Yeah, one more question, then I think we have to.
So in this picture, you've got the very distant galaxy cluster. You're seeing 3 images of it. Is that what you would see if you're at that convergence point? And the diagram on the left, where would you see that? Where would you have to be to see that?
Well, you have to be. So if this thing, I mean, in this kind of constellation, like if this thing is heavy enough, you would see this because you see, like if this is a galaxy or something, then you would see an image kind of coming this way. So you would have to look. It looks like it's in that direction, and you have other light that's coming in this direction. So it would look like it's going that way. So this is like in this situation, it would probably look something like this. Okay, so that's gravity. Now let's get to the waves. So this is kind of analogous to light waves, so electromagnetic waves, where you have your charges, and if they're just kind of sitting there and not doing much, you have your static electric field. But then if you kind of start wiggling these charges, you get this electromagnetic wave. And similar thing is kind of with masses, and except with masses, the situation you usually have in practice is that you have these 2 heavy objects kind of circling around each other, or kind of circling around a point in the middle. But the idea is pretty similar, that if these kind of oscillate, and that produces these gravitational waves. So and gravitational waves, what this means is basically it changes the metric, so it changes the distance between 2 points. And the first kind of hint that this is actually something that happens in reality came with pulsars. So these are neutron stars, which are kind of similar in principle to these white dwarfs, except even heavier. So more massive, more dense, and so the thing is, they usually have extremely strong magnetic fields, and a lot of the time they also spin really fast. And what that does is it kind of shoots radio signals out, kind of off the poles of this neutron star. And if this neutron star, because it's also spinning, this radiation beam is kind of like a lighthouse. If you're kind of in the correct spot, it will occasionally like kind of shine in your direction and then move away again, and then come again and again. And you see these quick radio pulses that can be as fast as, most of them are kind of like a couple seconds repeat rate. Some of them can be like milliseconds. And this was kind of weird at first. The first signal was called the LGM signal, the little green man signal, because people are like aliens, of course, because everything you don't understand is aliens these days. But eventually people figured out that this is probably what's going on. And then these 2 guys, Joseph Taylor and Russell Holtz, were basically doing a survey of trying to find more of these pulsars. And they found one and tried to just measure its period. And they couldn't really, because it kept changing. It changed by like a couple microseconds, but that is actually, these pulsars are, like the periods are incredibly stable. So this was actually like quite a big change. It usually changes like maybe a couple microseconds per year. But these change like several microseconds every couple of days. So this was kind of weird until they thought, well, maybe what's going on here is that there's kind of a second object here, that this neutron star is moving around. And if you kind of consider this, you can you can reconstruct the orbit this should have. So this is this shows here how quickly this neutron star we think is moving towards us and then away again. And you can tell that here where it gets around this what's called the periastron, where it's kind of getting the closest, or these two objects are the closest to each other. They're moving really, really fast. And then kind of they're slowing down. So you have a very eccentric orbit, like a very elongated ellipse, not really like the circle-like orbits we have here. And from the fact that it's so, from the period and from the fact that it's so eccentric, you can actually tell that these two objects get really, really close to each other. So they go within like a few times the radius of our sun to each other. And they also didn't see them kind of this neutron star being occulted by this other object. So if you have a star and they go within a couple times the size of the star to each other, then you would expect that occasionally, like this neutron star should get behind the star and get blocked at least to some extent. And from the fact that they didn't see this, they could conclude that the other object also must be very small. And from kind of the estimate of the maximum size they could derive, and from the mass that it should have, they could also tell that this must be another neutron star. So now you have two extremely dense, extremely heavy objects really close to each other and moving, and they figure out that if this is happening, then they should emit these gravitational waves. And these gravitational waves should carry away some of the energy, and that should change the orbit very, very slowly. And so for some years, they basically observed at what times this neutron star would reach this periastron, so the closest point to this other object. And they measured this for a while, and they could see that this actually changes, and the black dots here are what they measured, the change in the timing of this periastron. And then the line shows you what you would expect if they send out gravitational waves. And you can tell it matches extremely well. So they got the Nobel Prize in 93, I think. I don't know if that's related to the fact that the timeline here stops suddenly. They probably were satisfied with the result. But eventually people picked it up, and so this is a bit older, this paper, but it continued matching really, really well. Yeah?
Do neutron stars emit light?
Well, they emit these radio signals, but not really visible light, only very weakly because they're so small.
So larger waves,
Yeah.
they emit that?
Yes.
Not visible.
I mean, probably they emit some, but it's too weak for us to see. I don't think anyone's ever seen a neutron star with visible light.
So how do we know that they are there?
Well,
Is it only by the gravity?
Well, from the radio signals. From radio,
Radio signal.
yes.
Okay, that means they emit light.
Yeah, radio, in the radio band,
They're
yes.
visible.
Well, I mean, not visible in terms of like visible light, but with radio, like they emit radio signals, yeah. Okay, so that was the first really good evidence that gravitational waves are actually a real thing that that exist. The problem is that neutron stars they're heavy, but they're not extremely heavy. So these signals are like the gravitational waves are probably too weak for us to be able to detect. So let's instead take some of the heaviest things in the universe, or the heaviest thing probably in our galaxy, and that are these so-called supermassive black holes. So this is a picture of the one at the center of the Milky Way that was taken with this very long baseline interferometry a few years ago. And what this almost certainly is that it is an extremely heavy black hole with like several million times or billion times the mass of the sun. And even before we had like a direct picture, we could tell that there must be something extremely heavy there by looking at the orbits of stars around it. So this yellow cross here is kind of where where we think this supermassive black hole is. And then this is a sped up picture of the movement of certain stars around it. And if you pay attention to this one here, you can tell it's, speeding up quite a lot. So there must be something extremely heavy pulling on it. And from just how close the star is, so this star is within like a distance a little bigger than our solar system. So it's extremely close, and that means this object must be extremely heavy and extremely dense. And it's the only thing that could really explain this is a supermassive black hole. Yeah?
Over what period of time was this dated?
So there's a date in the in the top there. So it starts in 95 and it goes to 2002, I think. So it's a couple of years.
And that's the center of this current,
Our galaxy, yeah. Yes. And that the people who, or one of the persons who was behind this here got the Nobel Prize like 3 years ago, I think. Oops. And now, what we also see sometimes is that, so we think that probably every galaxy has one of these supermassive black holes. And occasionally we see stuff like this where you have a galaxy here and a galaxy here and they're colliding. And this is, it's overall a fairly rare thing, but the universe is extremely big, so this happens actually quite a lot. If you throw enough galaxies together, some of them are going to collide eventually. And what should happen with these two galaxies eventually is that they will fuse into one combined galaxy, and then also those two supermassive black holes should be orbiting each other. And then you have kind of the same situation like with the neutron stars, except now you have these supermassive black holes that are much, much heavier. And so there should be this kind of background of gravitational waves from these orbiting supermassive black holes. And so, this was a prediction, so people tried to figure out how to find them. And so if one of these gravitational waves comes along, what it's doing actually is it will kind of change, it will bend space-time a bit. So if you kind of imagine you have, let's say, like a bunch of spaceships here, and they just continuously measure the distance between them by, for example, like sending light pulses between them, then what you should see is that one direction, will, for example, first contract, and then at the same time the direction perpendicular to it will expand, and then it will go the other way. So in this kind of case, you will have to imagine the gravitational wave is kind of going into the screen. So it's, the gravitational wave is going that way. So this is obviously very, very exaggerated. We're talking really about tiny, tiny fractions of the actual distance. Yeah?
It's light speed, and so it's only transverse.
Yes.
Quadrupole. So you never get ahead of it, so it's light speed.
Yeah, gravitational waves travel at the speed of light, yes. Which also means that these wavelengths are extremely long because the two supermassive black holes will orbit, they will have orbital periods of at least several years because they're so big. And so now if you imagine that, you're somewhere where there's just a gravitational wave traveling through, and you're looking at some very, very distant clock, what you should see is that, as space gets longer or expands, the light from that clock is going to take longer to reach you, and then when it contracts, it gets there faster. So if you watch this clock very, very carefully, and you have a very, very precise clock, you should see that kind of there are these little shifts in the times you see, where it's, it runs ahead now it's too late, too late, ahead, and so on. So if we just now find some really precise clock somewhere in space, that would be really useful. And they exist. They are these pulsars because normal pulsars, as I said, are already very, very stable in terms of their rotation period. But these millisecond pulsars that move even faster, that rotate even faster, that rotate once every couple of milliseconds, they are incredibly stable. They are as stable as basically atomic clocks now. They are some of the most precise timing objects that kind of naturally occur in the universe. So we now just basically take a neutron star and we just watch its orbital period and see if we see these time shifts. Now, if we just do this with one pulsar, there might be other stuff that's changing the orbital period. For example, maybe there's like a star moving along and it's just kind of dragging it along a little bit. It's pulling it somewhere, so the distance changes a bit. This can always happen. So there can always be like some changes in the timing from other sources. But what we then do is we don't just look at one pulsar, but we look at a bunch of them. And even if we look at two of them that are fairly like roughly in the same direction, they should be like their timing should be affected in the same way. But even though they kind of look close to us, they're actually like billions of light years away from each other. So whatever affects one of them shouldn't affect the other one. And now, if we look in the opposite direction, we should also see those shift in the same, at the same time. And there's even less chance that it's the same thing affecting both. And if we look at something perpendicular to this, so if we look at this one, well, as this distance here expands, this one contracts. So if the period of this one shifts one direction, this one should shift in the other direction. So we have now we have a control in the other direction. And so this is then what's called a pulsar timing array. So you just basically take some radio telescope, and the neat thing about this is it's actually really cheap to do this because you just take some radio telescope that's already there, and then you just watch pulsars for a bit. And then you build what's called a pulsar timing array. Yeah?
Do they all have to be in the same plane?
No. They are everywhere. It's just drawing that way. That is one thing. Like if you have like a pulsar over here, then this is not going to be affected. But that's also something you can incorporate into this. And so for something like 20 years, there were several collaborations doing these pulsar timing array observations and just watching pulsars. And then a few years ago, they announced that they actually saw the signal. So this is these blue dots here with the error bars are basically what time shifts or what correlation in time shifts they saw between different pulsars. And the x-axis tells you like the angular separation. So here they look at pulsars that are pretty close together. Here they look at pulsars that are kind of in opposite directions. You can see they are pretty well correlated. And then if you look at pulsars that are perpendicular to each other, you see this anticorrelation that you would also expect. And so this dashed line here is what you would expect if these gravitational waves exist. And this green line is what you would expect if this doesn't exist. It's just all random chance. You can tell it fits this prediction for gravitational waves much better. And this is actually enough to say, like statistically, that it's extremely unlikely that this is actually just a coincidence. Now we know there's gravitational waves, but we cannot actually kind of see the source of them. We just know there's gravitational waves from somewhere. They fit with these supermassive black holes. But can we actually like find a source where we can point somewhere and go like, okay, this thing must have been it? And we can do it, and that's where we get to interferometers. So the idea is basically you have a laser here, and then you have a mirror here that lets pass part of the light through, and part of it gets reflected this way, and then you reflect it back, and you shine it on a screen or a photo detector or something. And what will happen then is if these two light rays take exactly the same time, then these waves overlap perfectly, and you have an increase. But if they're shifted by half a wavelength, then you would have a maximum from one wave coincide with a maximum from the other wave, and they will cancel each other out. And that's how you get these kind of interferometry patterns. And now, you don't do this at just one place, you do it at now basically 4 places. So there's these LIGO interferometers one's in Washington State, one is in Alabama. There's one under construction in India right now, but I don't think it's running right now. There's Virgo, which is kind of the same idea in Italy, and there's Kagra in Japan. And this is what one of the LIGO detectors looks like. So they have these really long arms so these are vacuum tubes, and they have kind of a big mirror at each end. And now a way to improve this is you actually add an additional mirror here. So now you still have your laser shooting at this mirror, gets split up, and then it goes in here. But this mirror here actually, it is set so that it lets light through in this direction, but if light comes that direction, most of it, or almost all of it, will get reflected back, and only a tiny fraction of it will kind of make it back. So the light actually gets reflected hundreds or thousands of times between these before it actually makes it out again. So you're not running the light once through each of these arms, you're running it hundreds of times. And so that way you get effectively, you build a much, much longer arm than what you can actually construct. And you do this twice, then you combine them again, and you have a photo detector here. The thing is, these mirrors, you want to keep them as stable and as, you don't want any vibrations on them, obviously, so you try to basically have them almost like float freely in space. That would be the ideal thing. But that's not going to happen. There's always going to be like something shaking it a little bit. So they just came up with the next best solution, and that is they built this really complicated pendulum. And the idea behind this is you're not going to keep it perfectly still, but what this pendulum does is if there is vibrations, these vibrations will happen at a very, very precise, at very specific frequencies that we know. So we know if there's movement at a certain frequency, then that's just noise, and that's I don't know, like a truck driving past or something. But if we see vibrations at different frequencies, then that might be a gravitational wave signal. And they were so nice to make a little video showing how this works. So let's go. So again, you have your reflections here. They don't show the thousands of times reflections. And so here the light gets combined, and they set it up so that in the natural state the light will cancel each other out perfectly. But now if you kind of start moving these mirrors, then the difference, the phases will change, and you have them occasionally. You will get a signal, and from the brightness of the signal, you can tell how much in or out of phase the two signals are, and you can measure how much your arms are expanding. And okay, and so they were waiting for something to happen, and in 2015 they actually saw something. So this is basically how much expansion of these arms they measured in two of the LIGO stations, because unfortunately the other ones, Virgo was offline and Kagra wasn't built yet, so you only had the two LIGO detectors. And so on the left is the one in Hanford in Washington, I'm sorry, it's in Louisiana. And here's the blue one here is what the one in Louisiana measured, and then the brownish line is just basically taking this, flipping it around to correct for the fact that these detectors have different orientation, and putting it on each other, and you can tell that they look almost identical. And from that, again, you can you have a good hint that this is an actual gravitational wave signal, because you don't expect anything, you don't expect the same kind of noise in Washington and in Louisiana at the same time. Now, interesting thing is to look at the y-axis here. So this is the strain. So how much did these two detector tubes actually change? And it is 1 part in 10 to the minus 21. So these are tiny, tiny changes, smaller than the size of an atom. But because you're shooting the light, you're reflecting the light hundreds of times in this arm, it actually ends up with a change in distance that is actually measurable. And
how much do the amplitude of these waves compare to the G of Earth?
I mean, it's not really comparable, because you're talking about changes in gravity, and the gravity of Earth is constant.
But there is amplitude of gravity. Gravity wave has an amplitude of gravity.
Yes.
Field. Okay. this amplitude, if you want to compare it to
Oh,
the
it's-
value of G,
It's tiny. I don't know the number, but it's tiny.
like
Um,
any value, any.
I would have to look it up, but it's tiny.
If this helps, the figure was in a LIGO experiment, like you said, 2015. They measured a distance that changed 1/2000th the diameter of a proton. They were
Yeah.
able to measure that.
Yeah, that's the change in length of these arms. But if you're talking about strength of gravity, I don't know the number,
Yeah.
but it's a tiny, tiny amount. So this is a signal they saw, and you can actually figure out quite a lot of what kind of thing produced this. And okay, first of all, this is what they kind of figured out must have happened. So this is simulation, if you run a general relativity simulation. So at the bottom here is the signal you would see in the detector. It kind of goes on for longer than what they actually saw. But they're orbiting, they're sending out these waves, and similar to what happened with these neutron stars, these gravitational waves radiate away energy, and so because of that the two black holes get closer to each other, they orbit faster and faster, and eventually they merge and the signal stops. And because they're orbiting faster and faster, the frequency of the gravitational wave signal changes. And that's what you can see here. So this is at what frequencies do we measure at what times, and you can see there's kind of a fairly weak signal at a couple of hertz, or like what's this, like 40 hertz or so, and then it's kind of doing this chirp signal. So it's whoop. It's what it would sound like if you kind of put sound to it.
Are they detected by their effect on certain mass?
On the effect on the length of these vacuum tubes. They basically change the length of the vacuum tubes. And there's a pretty neat property that's called the chirp mass, which you get through this kind of complicated equation. But it's basically, it just depends on the masses of the two objects that are orbiting each other. And the neat thing about this is it's directly connected to the change of the frequency of the signal. So it's this kind of scary looking equation, but it's actually fairly simple. So this is the change in frequency. So how much does this, or how quickly does the signal pitch up? And then this is, just some numbers. We know pi, this is a gravitational constant, we know the value of that. This is the chirp mass, and then you have the speed of light, which we also know, and then you have the frequency. So just from the frequency and how quickly the frequency changes, you can already say something about the masses that are involved in this. And then from kind of more finer details in the gravitational wave signal, you can roughly estimate the ratio of the masses that are involved in this. And from that you can reconstruct, or you can calculate roughly the masses of the objects involved. And based on, first of all, from the masses, you can tell that they are the masses you expect roughly for black holes. And from the fact that they also reach pretty high frequencies here, you can tell that they also got really close. And from the fact that they got really close, you can also tell that these objects must be really small. So you have very small objects that are extremely heavy, and this can only be black holes. Yeah?
You said high frequency. How high? How many hertz?
What's this, like 256 is here, so this is like a bit under 200, I guess. So this is, you can kind of go online and kind of look for sound files where they kind of go like, if you played a sound at these frequencies, like this is in the audible range, you can actually hear this, like it's kind of like a chirp sound. That's why it's called the chirp mass. So this must be black holes, and
So the signal lasts about half a second? The whole
even less. So this one, this one was pretty short. So this is from 0.3 to, so it's like 0.15 seconds roughly. So it's a pretty short signal because the like the strength of the gravitational wave signal also depends on the frequency, or like how the period in which these two objects rotate around each other. So you basically only have a strong enough signal kind of in the last couple fractions of a second before they actually collide. That's why this signal is so short. And so from this we can, since then LIGO has seen a bunch of other black holes, and you can, so this is already outdated, so this is from 2020. So now LIGO sees gravitational wave signal like every 2 weeks, roughly. So it's become kind of routine, so no one makes these plots anymore because they're just becoming too cluttered. But you know, this is kind of showing you like what masses these black holes that LIGO sees has, and you know, you always have kind of these two that you start with, and then the ones that you get as a result. If you look closely at these, you could tell that actually, like the masses, the sum of these two masses is actually bigger than what you get, because a lot of the energy is radiated away in gravitational waves. Because it's these tiny changes in like the length of these interferometers, but actually like bending space takes a lot of energy. So in terms of the energy that's emitted by gravitational waves, it's actually on the order of a couple solar masses. So if you think of it in like the energy that gets radiated away, it's actually extremely bright. It's just in a form that is really hard to observe. Now, this was black holes. The unfortunate thing about black holes is if they collide, you don't really expect to see anything else, because I mean, it's black holes, they're black, so they don't really emit any light. But then in 2017, LIGO saw this, except it wasn't LIGO anymore, it was called Advanced LIGO at the time, because they did a bunch of improvements to the detector. And one of the things you can see, so this is, I cut these plots up a little bit, but now we can see signals that are several seconds long. And you can also, just from the plot, you can see you see a lot more detail. And also Virgo was running at the time. And so the two LIGO observatories saw this signal here, but Virgo didn't see anything. So this was kind of awkward. They probably wouldn't have done a lot with this, except at the same time, Fermi, this gamma ray satellite, also saw gamma ray burst from roughly the same direction. Or at the same time. So this area, so this is kind of a sphere showing you kind of, if you kind of build a globe of the sky, then this blue area here is kind of where Fermi roughly saw this gamma ray burst. And it's not very well localized. That's because they use an instrument here called the gamma ray burst monitor that's just built to just see a big part of the sky, but it's not necessarily good at actually figuring out where the signal came from. And then, because of this, this was quite a coincidence, the LIGO and Virgo collaboration went back, and they figured out actually you would expect Virgo to see something unless the signal came from a very, very specific direction. Then it would just be the polarization of the signal would be oriented so that Virgo couldn't see anything. And from that, you could tell pretty precisely where it came from. And that is this green line here. So this darker green, it says basically we're 90% sure that it's from somewhere in here. So now you had a gravitational wave and a gamma ray signal from basically the exact same time from roughly the same area, and that was quite interesting. So they sent out what's called an alert, which is it's kind of like an email list you can sign on to, where like if some telescope sees something interesting, they send an email to everyone, and then you can decide if you want to follow up on this. And a lot of people did. So this is a paper they wrote about this. And each name here is not actually a person, it's a collaboration. So behind it, some of these are like hundreds of people. So we're talking about thousands of people here. Some of these you may recognize. So there's Fermi, this gamma ray satellite, IceCube that I talked about last week, POG, HESS, ALMA. So all these, suddenly got excited, and we're just trying to figure out where does this gravitational wave signal in the gamma ray burst come from. And so this is not a very precise localization. So the first thing was we want to know exactly where we want to like search this part of the sky and see if there's anything that could explain this. And the first one that found something was this fairly modest telescope in Chile. And what they did, they basically took a catalog of galaxies in this area and just kind of looked at each of them one by one, and just looked if one of them if there was a new bright spot there somewhere. And they found it. So they found what's called a transient, which is suddenly like a big bright thing. And they told everyone else about it, and a bunch of telescopes were pointed at this. And first of all, they measured how the brightness changed. And this is as a function of time, how bright different wavelengths are. And you can tell, especially the blue light, so the fairly high or fairly short wavelength light, is dropping off extremely fast. And this is a faster drop-off than basically anything that anyone's ever seen. So, for example, if this was a supernova, then it should stay bright much, much longer. And also, this is, if you look at the spectrum here, so these are two different spectra with different telescopes, you don't really see any spectral lines. There's like this line, but that's fairly weak. But if it was a supernova, you would expect to see these lines from like hydrogen or magnesium and all that stuff. So this couldn't have been a supernova. It was something that no one's really ever seen before. And then they waited a little bit, and a week later or so, they actually saw that you could see some lines. So if if you look at this black line, ignore the red line. That's just the model they fitted that did just to show that it doesn't really work. You see there's this increase in emission here, but it's a really broad line. And what we think is happening here is the reason you don't see lines at first is because this substance is extremely hot. So the atoms in there are moving extremely fast. So if different atoms will move at different speeds, so they will all be Doppler shifted, so you don't have like a single line, it's all getting smeared out. But then if it kind of cools down, eventually they will get cold enough that you at least get these broader lines. So it's still smeared out, but it's slowly cooling down. So okay, we know there is something extremely bright. And eventually, much later, so this is day 75 and day 230, they pointed a radio interferometer in it, where they where you take multiple of these radio telescopes and kind of combine them, and that allows you to see very, very fine details. And they saw that there was this kind of big blob emitting radio signals, and then about at day 230 they looked again, and they saw that this had moved by quite a lot. It looks pretty small, but if it looked like this moved faster than the speed of light, which of course shouldn't be possible. And they figured out that really the only way this could be possible is if you have a situation like this, where you have a jet emitting here. So, and what you're seeing here is basically you're looking at this jet, but you're not looking directly at the jet, you're looking at it from the side. So what's happening is, you have something like, for example, you have light emitted when the jet is here, but then the jet is also moving almost at the speed of light. So you have kind of the light and the jet racing. So if then later you look at this blob, it's here, so it's actually much closer to you. So this makes it look, so the light emitted here will arrive much earlier than the light from here, or the light that you saw earlier. So that's why it looks like it's moving faster than the speed of light. So this was kind of finally the way to figure out what exactly was going on, because this could only be explained if there is a jet, but you're not looking directly at the jet, you're looking at about 20 degrees off. And this was a really big breakthrough, because it has long been theorized that at least some of these gamma ray bursts are probably from neutron star collisions. And this was kind of finally the big proof that this is actually true, because you saw the gravitational wave from a neutron star merger, you saw a gamma ray burst at the same time, and thanks to all these telescopes combining and looking at the same thing at the same time, you were also able to understand what exactly is going on, and you were able to prove that there are these jets. And there is a ton of modeling to get finer details of how exactly this works. But it's kind of a good example of how you actually combine different instruments to just look at the same thing. And that is basically what I want to end this on, the note that I kind of divided stuff into different sections just because that makes it easier to talk about one by one. But really what we do most of the time, we don't just use one of them, we try to combine them and look at the same stuff with any way we can figure out. And I hope that with this lecture series I gave a good idea of how this all works and what we're actually doing, and that we're not just looking at pretty pictures. So thanks all for coming. Okay, let's go through questions. Last chance.
So that last observation that you've broken down for us, did you say at the very beginning that two of the LIGO apparatuses saw a signal, but the third didn't?
Yes.
And so what's the explanation, if you told us, I'm sorry, I missed it.
Okay.
That third one not coming through?
So it's this. Okay, so basically, if you go back here. So this is like the the gravitational wave is polarized. Is like the changes in the space-time are perpendicular to the direction that it's traveling in. So if you if you orient your for example, like you have one arm pointing kind of out of the board, then that arm wouldn't see anything. Or if you kind of have your arms oriented at an angle so that kind of this squishing happens in the kind of affects both arms equally, then you also wouldn't see anything. So there are certain geometries where you either don't have a signal in these arms or they basically affect both arms at the same time.
Is that just a strange coincidence?
Yes, it was kind of lucky, yeah. Yeah?
You know, all these telescopes that are on Earth, and Earth is part of the solar system, and the solar system is part of the Milky Way galaxy. As we know that the solar system is moving about 200 kilometers per second in space around the center of the Milky Way galaxy. Is this been taken into
Yes.
account when observing everything?
Yeah, that is that is something I didn't get into, but there is a lot of things. For example, there's also a big thing is in a lot of astrophysics is foregrounds. Like there might be, for example, gas between you and whatever you want to look at. You have to take that into account. Yes. So there's a lot of stuff that will affect your observations that you have to take care of, and yeah, the movement of the Earth and the solar system is one of them. Yes. Yeah.
When a neutron star is collapsing into a black hole, the escape velocity changes. Now, I've read that escape velocity is higher than it is dark. Let's say higher than the speed of light. Is that correct?
Yeah, I mean, there's one way you can think about basically what a black hole does. It is so small and so dense that, your escape velocity, like to get out, you would have to move faster than the speed of light, and that's why you can't. That is one way to think of why black holes, like why you can't get out of a black hole, yes.
So that's theorizing, right? It's not measured. They don't really know. I mean, there's no way.
No, I mean, yeah, you cannot measure inside of a black hole, but you can measure fairly close to them with, for example, gravitational waves. So that is actually like a lot of theoretical physicists are actually now looking at kind of like this part of the gravitational wave signal, because this is when they are almost touching, or when they're basically touching. So this is kind of the most extreme case of black holes doing something that you can observe, and this is like you can test certain like additional theories about how gravity works in this. So there's like a lot of looking into what exactly is going on here for testing physics. Yeah.
And the other part was, what is Hawkins radiation?
That is so. The idea is basically what can happen is if you're like very close to the event horizon, where like if you just moved like a little step to the side, you cannot get out anymore. what happens according to quantum mechanics is that you always have kind of like what's called virtual particles, kind of like popping into existence and annihilating immediately after. And if that happens close to the edge of the black hole, then one of them could fall into it and just not get out. And then you would have the other particle could make it out, and then you would have this radiation. That's it is a prediction. It hasn't been measured yet, but that's the idea behind it. Yeah.
What can all gravitational waves tell us about a star or an object
Well,
in space besides size and?
okay, yeah, there's actually quite a lot more you can tell. So, for example, a way you can kind of show from the way that this, like, how this kind of very last part of the gravitational wave signal looks. For example, you can tell that whatever's causing it didn't deform. So that also confirms that it must be a black hole, because if, for example, a neutron star will, at some point the gravity will kind of flatten one side of it. So you can tell that this didn't happen here. So you can tell that. You can also measure the distance, because the gravitational wave signal, like as I said, you can figure out the masses of the objects. That tells you how bright, in terms of gravitational waves, it should be. And so by comparing that to what you actually see, you can measure the distance to that. And that's currently, there's attempts to basically measure the expansion of the universe with that. It's what's called a standard siren. It's basically the same idea behind a standard candle, where you have something, you know how bright it is, and then you compare it to the redshift. That's also being done. So if you kind of really dig into the signal, you can actually tell quite a lot about these objects. Yeah, back there?
I assume that there was no chirp associated with that gamma ray burst 17817.
What chirp do you? What?
I'm assuming there was no chirp.
Oh, there was. So this is what the signal looks like. So you can see it kind of going up here.
No, the other one, the gamma ray burst, the GRB 17817.
Yeah, this is from the gamma ray burst.
Okay.
This is a signal from the neutron star.
And was there a chirp from that also?
Yes. That's what you can see here. So this is showing you like how the frequency where it was emitted of the gravitational wave signal, how that changed over time. And it starts as a fairly low frequency, and then it goes all the way to, what's it, like 300 hertz?
So the chirp coincided with the moment of the gamma ray burst?
Yes.
Pretty much, or was there a slight separation?
There was a slight separation. I don't remember how big it was, but it's like it was not like absolutely perfectly coincidence, because it also takes some time for the gamma, like for this jet to develop, for example. But it was like very close in time and way closer for it to be a coincidence.
Related to that, there's light is massless, gravitons are massless, and one is angular momentum 1 because it's a vector thing, the other is angular momentum 2 because it's water fluid. And I know Einstein looked vainly for a connection between light and gravity because he didn't know what light was. And I know you're doing this, looking for simultaneity, like he was mentioning. Is there any speculation yet about the connection? Because you've got two boson excitations, which are both massless, and could be somehow connected in a hierarchy of some kind. And I have not seen any theoretical speculation on this connection yet.
Theorists will come up with a lot of ideas if you give them enough time. So theorists come up with a lot of ideas. It's just like a lot of them are. It is pretty clear that this gravitational, this gamma ray signal came from this jet, because that's, you have a jet that's almost pointing our direction, and is also interesting because this object was fairly close, like this neutron star merger was fairly close to us. So, yeah, it's basically just because the jet takes some time to develop. there's probably no like fundamental interaction between gravitational waves and light. If that's what you're asking.
Nothing yet.
Probably not.
This blue figure,
Yeah.
here, what are these, the dots, not that rays, the
Oh.
other dots in the figure, what are they?
Like this?
Yes.
That's just noise. You always have like some vibrations or something. Yeah.
But I see as their interaction, because when this line goes there, it gets brighter when it hits one of them, and it looks at the location of. I mean, is it an interaction between noise and? I'm just wondering what we are seeing here. I want an explanation what this figure is, because these are noise signals, like.
Well, yeah. I mean, you always.
I don't know what.
Whenever you measure something, you will have some kind of noise if you try to be really precise.
And when the line, this streak of line hits one of these noise, gets brighter.
I mean, so what can happen is just that you have a kind of a maximum in your gravitational wave signal and a maximum in the noise at the same time by coincidence, and then it amplifies the signal. That's just how noise works. Yeah.
Yeah, the scale of these distortions of space-time is really, really small. What would it take in the equations, the Einstein equations, or the fundamental constants of the universe to make it larger so that it might affect macroscopic people like us?
I mean, for like the objects emitting it, it's mainly depending on the masses and the frequencies involved. So basically, the higher the frequency, the stronger the gravitational wave signal is, and then obviously the higher the mass. If you want to get a kind of like stronger signal by kind of messing with constants of nature, I think you would have to make gravity stronger. But like a lot stronger. Probably strong enough that it would kill us. So that's not going to happen.
Right now it's like 10 to the minus 40 of electromagnetic force?
Yeah, something like that. Gravity is overall pretty weak.
Now, what if you had two black holes that were the equivalent of galactic masses hanging together?
So the problem with that is that these black holes would also be pretty big. And they cannot move faster than the speed of light, so that limits the kind of how the frequency with which they can orbit. So I would have to kind of look it up, but I don't think you would actually get that strong of a signal because the frequency actually matters like a lot. And there's also the problem with the wavelength involved, because if they orbit with a period of like, let's say days, then you have like days times the speed of light is the wavelength of your signal. So you would need a detector that is that size to actually see anything, which is going to be difficult. Yeah?
Now that these LIGO experiments are getting more sensitive, I'm wondering what the study of gravitational waves can tell us about the early universe or Big Bang. For example, should there be a background of gravitational waves from inflation or the Big Bang itself, similar to the microwave background?
Yes. Yes, and the way you would measure it is with a microwave background. So if inflation is the idea that in the like extremely, extremely early universe, you had an extremely rapid expansion of the universe. And if that happened, it should have produced gravitational waves, and you should see the signal in the polarization of the gravitational wave background. And there has actually been this was like 10 years ago or something, there was a collaboration called BICEP at the South Pole. It was a microwave telescope at the South Pole. And they actually announced that they saw this signal, but eventually it turned out that they didn't correct for like the dust. Dust that you're seeing can mimic a signal like that, and they didn't correct for this correctly, so it turned out to not actually be a discovery. But in principle, this is something that we should have, we could see in principle. We just don't. So yeah, you can see gravitational waves from the early universe, but you probably cannot detect. They will be extremely hard to detect directly. And I honestly don't know if there's a viable way to do that. Yeah. Yeah.
Back to the LIGO signals, please. We see there
This one.
So when it starts to decay, a signal, I think you alluded to it. Is this when you think the neutron, the black holes have come some critical distance apart and are almost touching, or I mean, the frequency continues to go up, is it not?
Yes.
It goes down.
Yeah. So
explain how that amplitude goes down, the frequency goes up, and you said they don't change shape.
yeah.
So if they're merging, during the merging process, they must have a dumbbell shape or something, or no?
Well, so they will, they have this event horizon around them, and so at some point they are going to be close enough that like their event horizons overlap. But like.
So their overall shape might have something like an hourglass shape or not?
Well, it's basically like two circles or two spheres that overlap. But like around each individual one, you still just have a basically perfect sphere.
Two overlapping spheres have a waist. That is
Yeah. That's what it would look like.
If that's the right model. Is that explained by that decaying amplitude, the higher frequency to the right of the maximum?
So this thing here, that's called the ring down, which is basically kind of what the black hole does kind of like right after merging. And that's really complicated to simulate, and to be honest, I don't know the details of this. But kind of like the very, very last kind of peak in this gravitational wave signal is also from influenced by the new black hole that gets formed. You can kind of see that in here. What is it? So if we skip to the end. Nah. Come on. So, you can see there's this kind of ring going out, and that's this ring down from like the newly created black hole. Yeah, in the back there.
Willie, could you create a stronger signal if you had two black holes whose masses were primarily W bosons?
So the thing is, it doesn't actually kind of matter what's inside the black hole, because it's always called like the black holes don't have hair, which is basically means that you can fully describe a black hole by the mass, the spin, like the angular velocity, and I think the charge, and maybe one other property, and like that's all that kind of matters for black holes. So what's inside there for someone on the outside actually doesn't matter. So if you put W bosons in your black hole, or you put normal matter in there, you get the exact same thing. So it's not actually going to do anything. Okay, I don't see any more questions. So then, thanks all for coming.